Okay, so today we have Craig Lawrie, who will tell us about the Macdonald index from geometry. Take it away.
Yes, wonderful. Thank you. It's always nice to be back here in the Quiver meeting amongst many friends. And so I am very happy to be able to tell you this kind of story that we've been developing over the last I don't know, 12 months or so. So we wrote one paper with Monica Kang and J Song, which came out over the summer, and then we have another, and I put some dots here to emphasize that I think there's a lot to do in this area, and I hope we will do it, and I hope other people will be excited and also want to be part of this. So, okay, so this is the quiver meeting, so I should show you the quivers, no? But unfortunately, you're all going to be very disappointed because there's only one quiver and it's on this slide. But hopefully, with this little teaser, it will carry you through. And I think there are some interesting questions related to quivers, which I'll try and highlight here. So this talk will be about 4D n equals 2 SCFTs. And as we know, such theories with sort of sufficiently large supersymmetry have lots of interesting physics. So in this meeting, a topic that has come up many times is the moduli space of supersymmetric vacua, which is known as the Higgs branch, that particular branch. And a nice fact, which connects Higgs branches of such theories to quivers, is that you can often rephrase the Higgs branch of a theory as the Coulomb branch of some kind of quiver, where this quiver is now a 3D quiver. So this has been a very powerful technique that I think many people in the audience have developed and worked on. Um, However, the Higgs branch is one sector of protected operators of a 4D n equals 2 theory. You might also be interested in the other sectors. So what is going on? So there's the Higgs sector. There are other sectors which are sometimes called the Hall-Littlewood sector, the Schur sector, and then there's sort of a generic protected half BPS, eighth BPS sector. And in each of these sectors, there's sort of some technique, some object which counts operators in some way. Maybe it counts them with signs, and we would call it an index, but some way of counting the operators that belong to that sector. So the Higgs sector, you have the Higgs branch Hilbert series, which is just the Hilbert series of the ring associated to the Higgs branch. You have a Hall-Littlewood index in that sector. In the Schur sector, you have the Macdonald index, which, of course, when you unrefine a certain parameter, you recover the Schur index, giving the name of the sector. And in this most generic case, you're studying the superconformal index. So what do we do? What am I going to tell you about today? So today, I will explain how we argued that the Macdonald index, which captures the Schur sector, is actually the Hilbert series of a certain geometry. And that geometry is related to the Higgs branch. So a priori, this could be quite surprising because the Schur sector, for example, contains the stress tensor, which is not part of the Higgs branch chiral ring, and it contains a whole bunch of operators which are very disjoint from the Higgs sector. So why? Why should something like this be true? Why should I be able to use something related to the Higgs branch and recover information about a completely different sector? Um, So now there's sort of an obvious question which I pose to everyone who wants to think during this talk. Um, if there is a refinement, which I will explain what that means, of the Higgs branch, which allows us to access the Schur sector of the theory, and we know that the Higgs branch is just related to the Coulomb branch of a particular 3D quiver, what does this refinement mean on the quiver? Is there some interpretation of that? So this is a good question to keep in your mind as I go through the talk, and I'll come back to it again at the end. In particular, we will study some theories whose Higgs branch is C2 mod Z2, and I will explain the refinement in that case. And here's a little quiver for C2 mod Z2, which will be relevant later. But this is the
What's
only
what's
quiver.
the wiggle?
It's the orthosymplectic version of C2 mod Z2. I don't know why I chose that one. Uh, so it's the charge 2. Yeah. Okay. So for the people in the know who maybe just want to cut to the punchline immediately, I'll give you a little spoiler. I invite no questions on this slide because the questions you ask will be answered in the remainder of the talk, I hope. So what we proposed in this paper is that for each 4D n equals 2 SCFT, there exists an object, in this case it's a bifiltered ring, and I'll explain what that means, such that the Macdonald index, which counts the operators in the Schur sector, is obtained by taking a Hilbert series of a certain object related to that ring. Um, Furthermore, the Higgs branch of the 4D n equals 2 theory is one takes the ring, one takes the spectrum of the ring that defines for you an algebraic scheme, and then one reduces that scheme to a variety, and that underlying variety is in fact the Higgs branch of the theory. So in this sense, this ring R is some kind of schemification of the Higgs branch, whatever that might be. So the goal in the talk today is that I will explain and unpack what this expression means, what J infinity is, and so on. And that will be sort of the first half. And then I'll try and give evidence that these expressions are actually true for a variety of, in this case, mostly Argyres Douglas SCFTs. Okay. So you might be questioning about why I said the word geometry and then all of a sudden I'm talking about bifiltered rings. Maybe I'm misleading you here. But as we know in algebraic geometry, we know that if I start with a ring, I can take the spectrum of that ring. And this allows me to define what's called an affine scheme. That scheme is also bifiltered because of the bifiltration on the ring. So really what we're talking about is a scheme which reduces to the Higgs branch as a variety. Okay. Right. So there has been some work relating similar or related objects before that I want to highlight sort of immediately. So for the A1, A2n theory, we're actually in the A1, A2n, several of these symbols, in particular the GR trivializes. This correspondence has been conjectured a couple of years ago. And in fact, you can prove it for the A1, A2 theory. And hopefully later I will convince you why why this is challenging, even the A1, A2 theory, which should be the simplest theory imaginable. Okay, and similarly for the A1, D2n plus 1 theories, a similar correspondence was studied in this paper, which I think came out about 2 weeks before our paper, much to our surprise. And there, the ring that they're considered was not a priori, at least the same as the bifiltered ring we consider, but it was what's called Jou's C2 algebra of the associated VOA. And I will explain in some places the connections between the C2 algebra and the ring we define, although it's not entirely clear what the connection always is, in particular relating to the bifiltration. Okay. Okay, so now I will try and explain what this object, this Hilbert series that we want to compute is. And this is the point where I encourage you to ask questions throughout the next slides, so that everyone gets a nice understanding of what this expression is. Okay, so the first object I said is a bifiltered ring. So what is a bifiltered ring? A filtration on a ring is sort of an extension of the notion of a grading on a ring, where the grading doesn't quite work. So this is a weakening of that concept. So essentially you have a sequence of subgroups. In this case, it's a bifiltration. So I have two indices and they satisfy certain relations. Those relations are roughly that if I have sort of an element of degree, p and an element of degree q, of p and p prime, and I multiply them, I get an element inside of the filtration p plus p prime, and so on. So they're fairly tame things. Now, this is easier explained by way of an example. So let's just take the free ring in two variables, x and y. We can define a filtration by taking all polynomials whose degrees are less than some numbers. Now you can sort of convince yourself that all of these axioms for the filtration are satisfied. All right. And this is sort of the idea to hold in your mind for what a bifiltration is. Now, in principle, this seems kind of ugly. If I specify a ring for you and you have to write down some kind of subgroups which satisfy all these axioms, maybe you balk, maybe you say, that sounds like a sort of tedious technical exercise. Well, there's actually a very simple way to construct bifiltered rings where you more or less don't have to worry about the filtration at all. And this is what we will use extensively. In particular, we can assume that we start with a bigraded ring, which is just the ring in sort of n free variables. The fact that it's bigraded tells you that the ring decomposes into a sum of subrings, like this. Now let's consider an ideal which belongs to S but is not necessarily bihomogeneous. In the cases we'll talk about, it will actually be homogeneous in one of the degrees and not homogeneous in the other. Okay. Then the quotient ring S mod I is not bigraded. It's obvious why this is true because if the thing is not homogeneous, then the relation connects terms of different degrees, and therefore it doesn't make sense that it is homogeneous. So let's jump to another example. I take again the ring in two variables, x squared plus y cubed with these degrees. You see that the term x squared has by degree 6, 4, and the term y cubed has by degree 6, 3. So, for example, if you look at such decomposition, the element x squared would be inside of S64, and the element y cubed would be inside of element 63. And so the relation does not keep you within the thing. And so this destroys the bigrading. Okay, I told you that such a thing is bifiltered instead of bigraded. And indeed, the bifiltration is just
it stays non-normal.
It stays non-normal.
The bigrading keeps this property.
The bigrading keeps the property, or you mean the bifiltration?
Of having a non-normal variety?
Yes. This will stay the same.
I see. Okay. Thanks.
Yeah.
Normality, is this related to having a grading or not a grading? I think it's independent notions,
yes,
no?
yes, exactly. It's a different structure you put on the same ring, and the normality is a property of the underlying ring. Yes, exactly.
Okay. Yeah. Okay, fine.
Perfect. Very good. So you can define the bifiltration in this way. Now what I will do for the rest of this talk is I will not write down the explicit bifiltration, but I will say if I take a graded ring like C and n variables and I quotient by an inhomogeneous ideal, then there is an induced bifiltration on the quotient ring, and I will assume we always use that bifiltration. This will actually be a kind of subtle point, as we might see later, but in general, this will be the rule.
Do you really need the negative degrees? Because you always write sum over z and...
Yes, I wrote this earlier, and I wondered if someone would ask this question. In all cases that we consider, there'll always be positive degrees. And yeah. Okay. So we'll use this construction ubiquitously when we're talking about 4D n equals 2 theories. Okay. So I've been talking about bifiltered rings, and I've been talking about Hilbert series. And one of the things that you need to know is that a Hilbert series is only really defined for a graded ring as opposed to a filtered ring. What does a Hilbert series do? A Hilbert series over a polynomial ring, it counts monomials of a certain degree. Of course, this implies the existence of a grading, which tells you what that degree is. In a filtered ring, you lack this concept. So we need to understand how we deal with that. And that brings us to the next symbol we want to learn, which is this GR that appears in the Hilbert series up here. So any graded ring, by definition, has a decomposition into a sum over subparts. Okay, and it's just a fact, which I will hopefully show you, that if you start with a bifiltered ring or an n-filtered ring for arbitrary n, then you can construct what's called the associated graded ring, which is just a graded ring with the same number of gradings. So how do you do this? Well, you have to define the decomposition as a direct sum of the associated graded object. So you have to define each element of the sum. And roughly speaking, you define it as the elements of the filtration, which are sort of new at level PQ, and not the ones that come from the previous level. So that's all this kind of fancy picture is doing for you. That is, if we go back to our previous example, if you take all polynomials of degree less than equal to PQ, that defines a filtration for you, or a bifiltration. The associated graded is then the PQ element of that is just all polynomials with degrees exactly P and Q, because we've quotiented out by the other stuff. So this tells you that the associated graded is just C of x and y, with the standard grading x is 1, 0 and y is 0, 1. So in some sense, this was not a very exciting example because I started with C of x and y, which we already know is naturally bigraded. I constructed the filtration and showed that you recovered the bigraded thing. But
because so the slide starts with graded ring, which is like a one grading, and then you always mention the bifiltration and the bigraded thing. Is there a reason why everything is bi?
so for us,
Like that's for example, like can you, if you have a filtered ring, can you always associate a graded ring without, like, or is this something that's special to bi things? I would think so, no?
I only focused on bigrading here because, okay, so there's a physical reason for this, which is that in the Macdonald sector, the Schur sector, you have two gradings, one of which is like the conformal dimension and one of which is like the Macdonald grading. So all of these things that I'm saying here actually hold for, like, you can define an N filtration.
Yeah, okay.
Yeah, like an analog of this kind
Yeah.
of basically compatibility of the filtrations, and the same thing. You get an N associated graded and so on.
Okay. Good.
So I'm
mathematically, like n filtered, n graded, all of this exists, and then what will be relevant is the bi.
That's exactly right.
Yeah, thanks.
Thanks for clarifying. Okay. So now we have learned what this GR is. The GR is a way of constructing something which is graded, which means that this Hilbert series operation here makes sense because I'm starting with something graded. Of course, you should have one little puzzle, which is that I've given sort of 3 fugacities to this Hilbert series, and yet I've been talking about this GR as a bigraded ring. So what's going on there? And to explain that, we have to pass to the final symbol, which is this J infinity. Okay. So J infinity is related to the notion of a jet scheme. I will mostly stay inside of the ring category instead of the scheme category, just to avoid overcomplicating the notation. But it seems that the concept of a jet ring is not really used. It's always the jet scheme. Okay. So here we just assume we have a polynomial ring over C. It has some variables and it has some polynomials. They can be homogeneous, inhomogeneous. At this point, we don't care about the extra structure. We just care about the basic ring structure. So I'm not assuming a filtration or anything now. We can formally expand each of these coefficients as a power series, and of course also expand the generators of the ideals, the FIs, as a power series. Here, okay, this is just a thing we can do. And once we do this, it allows us to define a new ring, which we call the coordinate ring of the nth jet scheme, which is a bit of a mouthful, so I will use the expression jet ring throughout this talk. So basically what you do is you keep all of the variables in the expansion up to n, and then you look at all of the ideals, which come from the coefficients of t in the expansion of the ideals that you started with. I'll show you some examples of explicit examples in just a second, but this is a thing that you can do. Okay. Now, this object, Jn of R, the jet ring, it's naturally comes with a grading, regardless of the structure on R. What is this grading? Well, the grading is just the degree of the jet. Yes, you can see that, okay, you can do a little bit of work, but only takes a second, to see that this thing decomposes into sum of subrings, where the quotients act on the same jet degree and so on. You can see this just from the expansion. So Jn of R naturally is a graded ring. And indeed, if R is bifiltered, or if R is n-filtered, then this jet ring actually inherits the bifiltration in addition to the new grading, which comes from counting the jet degree, which is just this degree here. In this case, I'm going to simplify my language, and instead of saying I have a bifiltration and a grading which are compatible with each other, I'll just say there's a trifiltration, even though one of those filtrations is kind of boring. Okay, this way. Okay, and now in the picture at the top we have a J infinity. So I should explain this, and this just comes when we take a formal inverse limit to large N of this jet ring, and this is the coordinate ring of what's called the arc space in algebraic geometry. Okay, so this becomes a bit of a mouthful, but let's just have a look at an explicit example. Let's take our same old friend with x squared plus y cubed. To work out the first jet ring, we expand x and y, and so we keep x0, x1 at y1, y0, y1. And we keep the coordinates up to, we keep the ideal generators mod t squared. So this is the t to the 0 term, and this is the t, the linear in t term. We can compute the second jet scheme. We have 1, 2, 3 relations now, and 6 coordinates. And you can start to get a feel for the fact that this grows kind of fast. So for the nth jet scheme, generically, there are 2n coordinates, and you have an ideal, which is generated by, I think, n plus 1 polynomials, which are essentially of this form. Okay, so the thing to maybe be convinced of is that this is a very concrete object. It might be quite an involved object, because as you go higher in the jet degree, higher in this value n, you get a lot of generators in the ideal, but it's a very concrete object. Okay, so now I think yes,
the infinity limit makes
yes.
it seem a little bit less concrete. Maybe is there a way of thinking about?
So in something like 2 slides, I will explain why we don't need to worry too much about that. So if you want to do something concrete, just to say it in a few words, you can always truncate to an nth jet scheme for something n. Alternatively, if you want to do something really analytic for formally n equals infinity, you typically don't work with the ring concretely anyway. But I have a slide on that in a few minutes.
Okay.
Okay. So we have this up. Oops, this way. So we started with a ring which was bifiltered. We took the arc ring construction that gives us a trifiltered ring. We took the associated graded, which gives us a trigraded ring. And now it makes sense to compute a Hilbert series, and we do. One of the things which is special about this Hilbert series is that in principle it involves three fugacities, but actually I've set two of them to be equal. And this is just the way it comes out. So I've set the jet grading, that's the new grading introduced by taking the jets, equal to the what I will sometimes call the conformal grading, and the t will be what I call the Macdonald grading. Okay, so now we have some challenges. I have an object. I've hopefully persuaded you that it's an object which you could compute. But there are some challenges. So here's some technical challenges. The first is that, as Philip sort of alluded to, J infinity has infinitely many generators and infinitely many relations. So how do you actually work with that guy? Another non-trivial thing is that J infinity almost always has sort of non-trivial syzygies. Syzygy, by the way, has been my go-to hangman word for the last 15 years. No one has ever survived it. So if you have non-trivial syzygies, then to actually do this computation of the Grosvenor basis of the Hilbert series, you must first compute a Grosvenor basis, and computing a Grosvenor basis is generally speaking fairly challenging. So there are results. This is like an exponential time activity in the number of generators, and we're talking about things with very large sets of generators. So this is a very non-trivial technical challenge. And then, of course, there's a conceptual question. I've told you that there's this bifiltered ring associated to an SCFT, and you can compute the Macdonald index through this Hilbert series. But I haven't explained in any way how to compute what is this bifiltered ring that you start with. So we'll come to that in a moment. So how many jets do we actually need? So this is sort of an answer to Philip's question. You could suppose that you have some ring where you have some degrees, and then you quotient by an ideal which may or may not be homogeneous. Doesn't matter for what I'm saying here. Now, the lowest order contribution of the coordinate xj alpha, where alpha counts the number of jets, occurs at order q to the degree under this the first bifiltration. I'll just say grading, even though one has to remember that there's always a filtration and associated gradient involved. Under the first grading plus the jet degree, and then there's the t for the second. Similarly, the lowest order contribution of the generator of the ideal Fi alpha occurs at q to the Ci plus alpha. So if I want to compute this Hilbert series up to a certain order, say q to the L, then I can see that is identical to the Hilbert series up to the same order of the L minus dth jet scheme, where d is the xj with the smallest first degree. So the smallest such aj in this kind of equation. So above that, at that point q to the L, they will start to diverge. Or above q to the L, they will start to diverge. But up to that point, they are the same. So if I care about it up to a certain order, maybe for practical reasons I actually want to compute something, then I can compute with the jet scheme, which has a lot, but finitely many generators of the ideal. So we can compute to sort of arbitrarily large order while working over finitely generated rings. Yes, but we might want to prove something analytically in the infinite limit, but that's would involve different techniques. So the conceptual question was, how do we actually find these bifiltered rings in the first place? So what we proposed is that there should be some kind of deep connection between decoupling in the space of CFT data, which I'll explain what that means, and that's somehow very important for the CFT. So this is an opinion which is sort of influenced by things like the conformal bootstrap, where if you explore the Ising model, there are certain terms that drop out of the OPEs, and this is very powerful for constraining the rest of the data of the CFT. example. There are also examples in 2 dimensions, but this is sort of a thing that we had in mind. So I'll explain a little bit what this means. So often what happens is that you take an OPE of certain multiplets. In this case, I'm thinking of kind of universal multiplets like stress tensors or flavor currents or this kind of thing. And what often happens is that when you take these OPEs, you find that operators which you expect to be there are not there. This could mean 2 things. This could mean either the operator itself is completely absent from the spectrum, or it could mean that the OPE coefficient vanishes. But in either case, this seems like a very special situation, and this is what we wanted to. This is what we thought was important. So, for example, if you take the stress tensor, which in the language of Dolan and Osborne is a C hat 0, 0, 0 multiplet, and I take the OPE of n plus 1 of these things, you would normally expect on symmetry grounds and so on that expansion would contain a C hat n over 2 multiplet. Now, for the family of Argyres Douglas theories called A1, A2n, this multiplet is absent. It's not there, as explained by these guys here. And you could translate this into an algebraic condition, which unfortunately I introduced a typo. Of course, it should be n plus 1 here, which is that x, you could just rephrase this by saying x to the n plus 1 is equal to 0. And indeed, that will be sort of the source of how we come up with the polynomials that define this bifiltered ring. Okay. Now, in general, maybe finding the decoupling in OPEs of Schur operators can be challenging in 4 dimensions. One thing that we find very helpful is that you can translate this question into a study of null relations in the vertex operator algebra, which is related by the SCFT VOA correspondence of these gentlemen here. I guess I shouldn't say gentlemen. Right. So, yeah. So what happens for A1, A2n, the associated VOA is m2 2n plus 3, so it's a Virasoro minimal model. And this theory contains a null state at level 2n, which takes this form. So this VOA has a strong generator. The strong generator is actually just the stress tensor. And you have this null relation that looks like you raise it to the nth power. Okay. So what we learn, or what we want to take advantage of, is that we can study null relations in the vertex operator algebra of the theory. This gives us polynomial relations in the strong generators of that VOA. And if we rephrase these as algebraic conditions, this gives us a candidate ring. And perhaps surprisingly, this works. Okay, so this is sort of the logic. It would be good, of course, to illustrate this by a number of examples, which is what I will now attempt to do. Okay. So let's start with the A2, A3 Argyres Douglas theory. I'm going to skip talking about the A1, A2n because this was largely done by the people I mentioned on the first slide. And some of the subtleties are nicer there. You don't have to pass to the associated graded. Even then, it's challenging. So the vertex operator algebra associated to the AK minus 1, AN minus 1, it's the W algebra. Yeah. And for the A2 theories, we're interested in what's called the W3 algebra. And this algebra has been studied in great detail by Agarwal, Lee, and Song. And indeed, they have a nice appendix where they did a very intensive computation and they worked out the null relations in the algebra. Maybe I want to digress for just one moment here because the calculation of the null relations in the vertex operator algebra, as some of you may know, is also a very computationally intensive task. You can put it on a computer, but it runs for an extremely long time. A similar thing can be said to be true about computing Grosvenor bases and thus computing Hilbert series of these rings, these jet rings. What seems to be interesting is it seems to be a lot easier to go higher in the computation of the Grosvenor basis than it is to use the techniques which you would use, with OPEs to compute the null states. So this is sort of interesting and maybe indicates that there's some technique which can simplify the derivation of the null states. Okay, so these are the null states. Now, I keep pressing the wrong button. So the strong generators of the W3 algebra, they're labeled W minus 3 and L minus 2. L minus 2 is the stress tensor, W minus 3 is another generator, which extends the Virasoro. The other objects, W minus 5, L minus 3, and so on, these are descendants. So if I only focus on the strong generators, I see just these three terms here. Now, these are the null relations which appear at the C equals minus 114 over 7 version of the W3 algebra, which is precisely the vertex operator algebra for the A2, A3 theory. Okay, so what we want to do is we want to look at these equations and we want to translate them into something algebraic, which is pretty obvious how to do. We take a bigraded ring in two variables, x and y. I'm going to give it the degrees 3, 2 and 2, 1, and that is obviously supposed to be a y. And then we consider the ideal x squared plus y squared and xy. So you can see here, there's two typos on this slide, which is very disappointing. So I'm letting y be L minus 2, so it should really be y cubed, and I'm letting x be w minus 3. So it should be, of course, x squared plus y cubed and xy. Okay, good. So this is a ring.
Where did the second grading degree come from? I mean, the 3 and the 2 for x and y, I understand, but why 3, 2 and 2, 1?
Oh, wonderful. So I have to start by defining, you've touched on a great point. I'm not telling you how to derive the grading just by looking at the null relations. I'm only telling you really how to derive the ring, and then I'm putting the grading on it by choice. So I'll sort of tell you where the grading comes from. The second grading is supposed to correspond to the Macdonald T grading. And now I know that L minus 2 is the stress tensor. So I know its T grading should be 1. And so I'm using that piece of knowledge to put this grading here, the 3, 2 and the 2, 1. So indeed, I'm really only telling you how to derive the ring explicitly and not explaining how to derive the bifiltration on the ring.
So Craig, are you saying that the grading does not depend only on the W algebra then? Only the first grading depends on the W algebra, and then for the second one, you need to know that it comes from a particular SCFT, and then you have to.
I think that's good. So I don't think it's true. I think that I think the second grading also comes from the W algebra. So this thing, what I'm doing here, where I kind of throw away the descendant terms, is sort of like constructing Jou's C2 algebra of this VOA. And there are a bunch of different filtrations that you can put on, well, on both the VOA and the C2 algebra that you get by looking just at the null states of strong generators. And it's my suspicion that the information of both gradings is contained inside of some of those filtration structures on the VOA. But this, I think this has not been shown, and I think this is an open question, how you derive the correct filtration structures on the ring from the thing. Yes, I'm using the information that I know about the W algebra, which is that the sky is the stress tensor and so on.
Yeah.
But in general, there should be a prescription which tells you this is how you derive the bifiltered ring. from the
So it's
decoupling.
not always one less, for instance. We have 3, 2, 2, 1.
I'll show you some examples where it's not one less. Exactly. Good. Okay. So, okay, and now the bifiltration is as we said, the one that comes from quotienting by the inhomogeneous ideal. Remembering that this is a y cubed. My bad. Okay, so the nth jet scheme, it has 2n variables and it has 2n plus 2 generators of the ideals, and they look like this very ugly thing. Now, if we want to determine the Hilbert series up to, say, order q to the 13, so q to the 13, I want to stress this is a fairly high order. So one of the ways of thinking of this as a high order is to think of the degree at which the relations first start to enter. So you see that the relation x squared, this guy in the first degree sits at degree 6, and the xy sits at degree 5 in the first degree, which is the one that's related to the q. So you see that by going up to q to the 13, we're already taking into account like syzygies and relations of relations of relations and so on, because those things start happening already around order q to the 6. So this is a complicated beast. It has 24 polynomials in the ideal. So typically we use Macaulay 2 to find a Grobner basis and do the computation for us. And this is the answer that you get. Kind of horrendous, but you see there is a lot of coefficients in here. And this all matches with the expected expression, which was worked out. So this expression indeed was worked out by Agarwal-Lee Song in terms of the W algebra, and then there are other expressions worked out in terms of like the refined character of the W algebra as well. So this is great. Okay, this is
So
one.
what's the motivation for putting Q for both the in the first two gradings? Because if I understand correctly, the okay, so what's the degree of x is 3, 2, and so 3, 2 would correspond to Q and T, right?
3, 2 corresponds to Q and T, yes.
Right. So and then the other Q, this is the jet thing, the first thing.
The first Q is the jet thing.
And so yeah, so what's the motivation for setting them equal? So you could in principle do it for arbitrary efficacies.
That's right. So we also worked out the these triply graded Hilbert series. Those don't really seem to correspond to anything too interesting. So the jet grading, in a sense, counts the descendant operators. So somehow setting them equal to each other is the way to kind of untangle, untangle the contributions of all the descendants. So one of the remarkable things, which I think we don't know how to explain extremely clearly, is why is the jet ring relevant at all in this discussion? So I told you how to derive the ring from the VOA. But what is this? What does this process of taking the jets correspond to physically in that 2D CFT? And it's related to computing the descendants, but it's not clear why that's the right thing to do, other than that it produces the right answer. So this is I think, a question which is sort of begging for a physical explanation.
The jet is making kind of infinitesimal variation
that's right.
around your initial variety, and then you're looking at what it is at first order and then second order, and you're
exactly
all of this, but then
exactly. This is what the jet does. So the first jet space is like the total space of the tangent bundle, and so on. Experimentally produces the right answer. It was remarkable to us. Okay. Now we can continue to play the same game for the A2AN algebras for a larger n.
So actually, I have one more question here. So the ring that you get out of the VOA is like physical, right? You really know the operators in principle, which are involved. And so then in the jet space, also these are still operators that are somehow or would you say that it goes beyond this? Are they no longer operators in like the
So
existing?
I think the objects in the jet space are like derivatives of the
Yeah,
strong.
exactly. It sounds like, yeah, you just
Exactly.
somehow, yeah,
Uh,
yeah.
So,
So
that's what's
fine to look at them like it's a okay.
so they should be there. I mean, the index will see them, so it
Yeah,
makes
yeah,
sense.
exactly. So then, yeah, okay.
The fact that the right way to reconstruct all of the information of all of the derivatives is the
Yeah.
jet is, well, a nice fact. Okay. So I said earlier that computing the null relations in W algebras is kind of a challenging thing. Luckily for us, one of our collaborators, Chewan, had already gone through this difficult challenge, and they have a very nice appendix in this paper here, where they compute all the null relations up to level 9. So we can do examples up to n equals 7, so up to A2, A7, and actually compare them with known results. For higher than A2, A7, we don't have a VOA derivation. However, we can, be inspired and write things down for A9 and A10, and these things also work. So in some sense, that's then a challenge for on the W algebra side to reproduce these statements. So if we know the W algebras, we can derive the rings. So again, you look at the strong generators. Say I want to do the A2, A4, which is C is minus 23. Again, I have y cubed plus x squared. And now here I have xy squared, and then everything else is gone. So I just care about this term and these two terms. And I can go through this process and I can derive the rings. And I would derive in this way that the rings for these guys are like this. The coefficients I want to emphasize.
In that example, wasn't there another C equals minus 23 right at level 7? What happened to that one?
Yes, that's true, but it does not contain any terms which are only strong generators.
Ah, I see.
Yeah. Good catch. Okay, so we derive these things. And I want to emphasize here, if you're looking at these coefficients, the coefficients are very important. In these cases, in particular, things like A2, A4, you can reabsorb them by rescalings. But once you start getting to A2, A6 and A2, A7, the coefficients, of course, change the answer for what is the Hilbert series of the jet scheme. So one must be careful about this. But if one is careful about reading it off, one gets these answers. And you can compute their Hilbert series. I don't really expect you to read these complicated expressions, but one thing which is nice is just to compute them, to see that we can compute them up to a fairly high order. So these were worked out in this paper by Agarwal Lee Song up to around order q to the 9. So you see, we go, in this sense, we go much beyond. But yes, we can also compare with expressions for the refined characters of the VOA, and these all seem to match nicely. Okay. Another example is the A1D3 Argyres Douglas SCFT. Now this is where I draw us back to that little Z2, C2 mod Z2 quiver that I drew at the start, because the Higgs branch of the A1D3, and more generally the A1D2n plus 1, is C2 mod Z2. Okay, so I write down a ring. In this case, I'm not going to derive it from the VOA. I'm just going to write it down. But you should see this nice paper by these guys here, who recently studied this from the perspective of Jou's C2 algebra. So in this case, we take this equation, we take the degrees to be this. Okay, this is a choice, I'm just telling you. The bifiltration is the usual one that's induced by quotienting the inhomogeneous ideal. And then you notice something else. I told you the Higgs branch is C2 mod Z2. You remember that that has an additional SU2 isometry. So the theory has an SU2 flavor symmetry. And we can add an additional grading which captures that flavor symmetry. You can then compute the Hilbert series Now it's in fact quadruply graded because you're including the grading of this extra grading. And you get this beautiful expression here. And well, I don't think you'll check, but I hope you will take my word for it that all these decompositions of the characters of SU2 are precisely the refined Macdonald index for A1D3, which was computed some time ago by Buiken and Nishinaka from the field theory perspective. So even in cases where there's a non-trivial Higgs branch, unlike the A2AN, where the Higgs branch is just a point, we also seem to find the correct answer by doing this construction. There is a bit of a puzzle here. If you think of the vertex operator algebra associated to A1D3, you know it has three strong generators, which correspond to the three elements of the adjoint representation of SU2. Those strong generators are X, Y, and Z. So here, for some unclear reason, I've introduced a W, and I've given W exactly the gradings that I expect to be the gradings of the stress tensor. And then I've imposed this condition, W minus XZ plus Y squared, which is essentially the Sugawara condition on that the stress tensor is related to the flavor currents. So why did I do this? Well, as rings, you can see that this W is sort of irrelevant. I can take the W, I can solve the first equation, I can plug it back into the subsequent three equations in the ideal, and I get this ring R prime. Now, this R prime is isomorphic to R, and of course you can take the bifiltration that we define on R here, and we can push it through this isomorphism to define a bifiltration on R prime. However, this bifiltration is unrelated to any bigrading on C X, Y, Z. So for example, if you were just to forget about W and assume the grading of X, Y, Z is 1, 1, 1, 1, 1, 1, you would get the wrong answer because that's not the right filtration. So the choice of filtration, I mean, sort of obviously the way I've explained it, changes the answer for the Hilbert series. So for some reason, introducing W allows the bifiltration of interest to be defined as coming from the bigrading, which we defined on the base ring C of XYZW.
So how did you decide to do this? In other words, this is because this is just what worked, so to speak?
Yeah, exactly. So a large part of this was sort of experimentally doing it. So the reason we did this is you could start with the ring R prime, which is also the thing that Beeman R prime, which Beeman-Rastelli wrote down some time ago as used C2 algebra for this theory. And when you try and compute the Macdonald index, you find that the stress tensor is missing. So you want a term which looks like Q squared T, and you don't have it. So we went back and we said, well, if the stress tensor is missing, we know that the stress tensor comes from the Sugawara. So we put it in and we see what happens. And then you find that everything just unfurls and it starts matching to way higher orders than you expect. Naively, right? Usually you would think if you cracked, one term, you're going to introduce problems at higher terms and you have to keep introducing corrections and so on. Surprisingly, this doesn't happen. It seems that adding the stress tensor in this way is sufficient in this case to produce the right answer. Of course, we could also have taken R prime and said we'd like to put a different filtration on our R prime and so on. Yeah. So this does bring me to an important point, which is the two rings are the same as rings. They're the same as the C2 algebra as a ring. But it's clear that the bifiltration structure is very important, and I would like to know what this is. What is the correct bifiltration from the VOA perspective? Which in some sense should tell us why the right thing to do is to add the stress tensor explicitly, even though it's not a strong generator. Okay. So I'm going to do one more example just for fun. So this is an example of the A1, A5 Argyres Douglas theory. The Higgs branch of this theory is C2 mod Z3. So we're going up in complication in Higgs branches. And again, we just write something down. We have some degrees, we have a non-homogeneous ideal. You can see we're doing the same thing again. We're introducing a W, which is the stress tensor, which has the degrees necessary for the stress tensor. But then, yeah, these are different. And you see this is, yes?
Can the W be eliminated from the ring? It's not obvious to me.
Yeah, yeah. Here I don't think it can. Here I think it's actually necessary.
Okay.
Oh, yeah. And you see in sort of also answer to Antoine's earlier point, you see that the two, the Q and the T gradings are now not different by one, but they're actually the same.
They're also not integers.
They're also not integers, exactly. There's no, everything I did so far was integers, and you can always rescale the X and Y.
Yeah, of course.
So on. But somehow, in some cases, they're quite naturally not integers. You can see that if you look at the reduced scheme here, it just reduces to the solutions of xy plus z squared equals 0, which is the C2 mod Z3 singularity, as expected from the Higgs branch. And you can do the computation, and I realize my screenshot's a little bit blurry, but okay. You can do the computation of the Hilbert series, and again, you get some large monstrosity. It looks like we only go up to q to the 7, but now you remember they're half integers, so this is something like q to the 14. And this matches with, again, the known expression for the Macdonald index. So, to summarize a little bit, in this paper from the summer, we proposed a collection of bifiltered rings for a bunch of Argyres Douglas theories. This list has grown a little bit now, and maybe in the next paper, which will hopefully be not too far away, those will appear. But these are the ones we put in the paper. And the shocking fact is you just take these polynomial equations, you compute the Hilbert series of the associated graded to the arc ring defined by these polynomials, and somehow you recover the Macdonald index. So yeah, this is the result that I wanted to tell you. I think a nice fun thing to do is to understand where these polynomial equations come from, including the filtration in other examples. For example, the examples we chose here had very simple Higgs branches. They were either orbifold singularities. More generally, we can do C2 mod Zn by generalizing this case, or else they were trivial. The first 1, 2, 3, 4, 5 rows here has the Higgs branch just being a point. So it would be nice to have some more complicated examples, say where the Higgs branch is a minimal nilpotent orbit. But of course, then you enter a lot more variables, your Grobner basis computation becomes a lot more difficult, and you maybe are forced to do something analytic. Okay, so since I have 1 minute remaining, I would like to summarize. So what we did is we proposed the existence of a certain schemification of the Higgs branch for any, in principle, any for dn equals 2 SCFT, which allows us to recover information about protected operators in the Schur sector, not the Higgs branch sector. Well, in contrast to the Higgs branch sector. So the key object was that to the theory is associated this bifiltered affine scheme, and the bifiltration was very important for the structure. And this is a thing which reduces to the Higgs branch as a variety. We proposed a bunch of these schemes for a variety of Argyres Douglas theories, which we typically derived by looking at decoupling conditions in OPEs via the medium of the VOA. But ultimately, it's a 4D thing. When do terms decouple from an OPE? And in each cases, we could do a computation which worked to perhaps far higher orders than we would naively expect from the from the, shall I say, simplicity of the computation required to work out the polynomials or the ring. So yeah, this is I find this very exciting. The fact that all of this information is captured in this geometric object, and I emphasize it's a geometric object. And yeah, it would be good to understand more. So yeah, thank you, and I will stop here.
All right, let's thank Craig. Do we have questions? So
One maybe silly question. Last week, Nicholas Garner told us about a filtration on the BOA having to do with unitarity of the parent four-dimensional theory. Any possibility this is connected?
I was thinking the same thing during his talk last week, and I haven't looked into it yet. So there are a variety of filtrations that people talk about on the VOA. There's the Lie filtration. There are a variety of filtrations. I'm not sure which one is connected. I think this is probably not too difficult to find out. But yeah, I was having the same thought last week as he suddenly started talking about filtrations.
ding ding. So when you take the VOA, there is this notion already of an associated ring, and then there is the associated scheme, and this is not generally reduced. And if you reduce it, then you get the Higgs branch. This is the standard law here. So this scheme that you get if you don't reduce, how is this related to the scheme that you obtain? Is it a different scheme?
So
I've said scheme too many times.
I'm growing used to it. So the associated scheme that you're talking about is in fact in the VOA language, it is the Schur's C2 algebra, or it's the spectrum of Schur's C2 algebra.
Yeah.
So in all cases that I know of, as rings or as schemes, they are the same. So the open question I think is about the bifiltration.
Okay.
But yes, in the examples, yeah, like for example, this guy here. So it's actually a bit subtle because in Beeman-Rastelli, oops, in this Beeman-Rastelli paper here, they claimed that the C2 algebra is this thing here, and then the associated scheme is the spectrum of R prime. In this later paper by Andrews et al., they claimed that the Schur's C2 algebra is actually this R here. And of course, they are the same as rings. So both are correct statements, but I think...
Okay, I understand. Yeah, okay. I somehow missed this point. Okay, cool.
Yes.
Also in the VOA setting, it's very hard to find a grading and all of this. Like it's a really tricky thing. So I guess the filtrations is what it's all about there. Finding them and yeah, so nice stuff.
I haven't been able to detangle yet, which are the right filtrations.
Yes. Cool. Do we have more questions for Craig?
I have another, I guess it's a naive question. So at the end, you said that very quickly the computations become very hard, but so even for a simple thing like I don't know, Lagrangian theory, SU2 with 4 fundamentals or stuff like that, is there something to say, or is it?
Well, so
is it too hard already?
I think it's already hard. So I have some very simple things to say about like H2, whose Higgs branch is the minimal nilpotent orbit of SU3. Unfortunately, this guy has 8 generators. And so you take the ring with 8 generators, and then you have a whole bunch of relations which are related to like the adjoint action of SU3. And then you start taking the jets, and it grows rather fast. So I didn't do long computations, but still it was difficult to go beyond like q squared, q cubed. So I suspect the SU2 with 4 flavors is in fact harder because of a larger number of generators of the Higgs branch chiral ring.
So at the moment, with your technique, you can, if the ring is simple enough, then you can go quite far in the expansion and further than the people doing index computations from the beginning. But then very quickly, at the moment, at least, you cannot really compute for any theory which is
yeah, that's right. So I think
high rank.
Exactly. So one of the things that maybe I want to emphasize is that this is sort of early days. And for the A1, A2 theory, for example, that I mentioned at the start, where the ring is given by sort of C of x mod x squared. For this one, there's this very nice result, which I mentioned right at the start, where some mathematicians actually computed the Hilbert series of the arc space analytically. Now, this is I sort of said I would mention this and I forgot. This is a super hard computation because you have to expand this. You have these infinitely many ideals, all of which are like coefficients in a binomial expansion. Then you have to analytically find a Grobner basis for this set of things. And this is something that they did. It's quite beautiful. And so I think there are grounds that one could do this in other categories, but it's hard. In particular, if you think about sort of x squared is equal to 0, you could imagine working over a matrix ring of 2 by 2 matrices and similarly talk about x squared is equal to 0. And now you're talking about a Higgs branch, which is something like, SU2 matrices. And so I think there's a lot of scope for doing analytic computations. But in general, they involve this very tricky problem of finding Grobner basis.
This is also another thing that sometimes computations we do by hand simplify greatly by having some symmetry, but the Grobner basis computation doesn't care at all whether there's a symmetry in the problem. So if there's more generators, no matter if they're in some nice representation, it's just gonna be worse.
Yes.
So it's a base problem in this whole way of doing computations.
Yes. And
so the jet procedure would break the symmetry?
The Grobner basis does.
I see. So
that's why if you compute if you compute the sum invariance, compute the Hilbert series from there, it's much easier than if you're given some ring and then try to do the Grobner basis computation to extract the Hilbert series. Very hard.
It's just that you have to choose a monomial ordering, right? And that messes up your symmetry.
Exactly. Yeah.
But then it asks
the
how
final
this
answer will also break the symmetry?
I missed the first part, sorry.
So if I look at the final, so the procedure is breaking the symmetry. Is it possible that the final answer would still transform nicely?
Yes, the final answer should be independent of how you choose the particular Grobner basis.
Well, so this gives a hope that you might try to somehow use the characters.
Yes.
We tried, Ami, to have Grobner basis preserving some symmetry, but in the end, it's. But that's why I'm very curious to see how this mathematician did it. So maybe you can send us this paper.
I will send you the paper. Yes, it's very nice, but it's extremely technical and it's very impressive.
But I thought it was impossible, so now I'm really.
I mean, I think if I remember right, they did it for the x squared case in full detail, but the x to the n is, I think they partially did the x to the n. I think they got like not the fully refined like with 2 gradings, but with 1 grading or something. But already like it gets hard. Yeah.
Good. Do we have more questions for Craig?
Craig?
Well,
May I ask you a couple questions, please?
For sure.
So, first of all, you did A comma A and A comma D. This is because the VOAs are known, right?
So mostly for the A comma A odd, um, we didn't really use the VOA actually. We know it has to be a schemification of C2 mod Zn.
Mhm.
And you know sort of you know it has to overlap with A1 D3 for A1 A3. And then we just wrote something down and it seemed kind of clear. One thing to do would be comparing to the VOA indeed.
And what about D comma D, for example?
Um, I think it's interesting. We didn't think about it.
And not because of a technical reason, or
No, I just yeah, as I say, I think there are a lot of examples which could be worked out probably without too much kind of trouble, at least sort of computationally. Uh,
Mm.
as long as the Higgs branch is sufficiently simple, it seems one can do the computations.
Okay. Another questions I have is suppose that you have a Maruyoshi-Song n equal to 1 description.
Mhm.
This you can use to compute the full index and then take the Macdonald limit, right?
Mhm.
Is there any relation that with this method to the n equal to 1 approach? Because there you know exactly which operator from the
Yeah,
Lagrangian, because you have Lagrangian, right?
yeah, exactly. Um,
You ever look at that?
no, it's a great question. We didn't look at this. So actually, since you talk about Mariucci song flow, I take the opportunity to talk about some other flow. But no, the answer is we didn't look at the Mariucci song type deformations. One thing we did look at is whether you can do like Higgs branch deformations. If you know that theory A flows to theory B under a Higgs branch deformation, how does this affect the ring itself? Um, in the examples we had, it wasn't so clear. And I think the thing we want to do first is understand like say DPSUN, like the examples which we have are like A1 D2N plus 1, which flows to A1 comma A whatever. And you can kind of see a pattern in what happens to the thing, but we don't really understand it yet. So we didn't because the A1 comma A2N is like the equation is just x to the n plus 1. And there are kind of a lot of ways to argue that you can obtain that equation starting from the ring for A1D D2n plus 1, which is this guy here.
Mhm.
So we started looking at flows, but there's not a lot to say yet, I think.
So you said this is a mass deformation.
So we thought about both mass deformation and Higgsing. This
Okay.
one is, yeah, this one was mass deformation, exactly.
Okay. Thank you.
All right. Do we have more questions for Craig? The more, the merrier.
I'm always happy for questions.
But okay, if there are no pressing questions now, then Sam.
No,
Oh.
this is a pretty simple question.
Mhm.
So you take the grading after the arc space,
Yes.
but and what you start off with is filtered. So is there a meaning to kind of doing it in that order? Do they commute? I
I
mean,
Right. They do commute. You could take the
okay.
associated grading before taking the arc space.
Mm,
Yeah, in practical reasons, I like to take the associated grading last because the way the associated grading acts is you take one of these inhomogeneous ideals and this is another kind of Grosvenor basisy thing. You then make a choice of sort of which one is less than the other under a certain ordering. And the answer in the end doesn't depend on that choice, but you make that choice and then you take the what's called the initial ideals of each of these things. And so somehow in practice, I prefer to think of taking this at the end. But I don't think there's I mean, as operations, they commute.
Okay. Thanks.
Cool. Good. More questions for Craig. Okay. So then I'd say let's thank Craig again
Yeah, thanks a lot.
for
Thank
this
you.
nice talk. And we can go off the record.